All right, let me move on with the data path, which has a FIFO and a serializer and a set of driver stages, driving the data signal, valid signal, and the clock and track signals. So starting with the serializer, there are multiple ways of building serializer. All of them take a parallel set of low rate input data and serialize it into a single stream of really high rate output. Okay, and I said there are multiple ways, but one way is to use a tree structure of the tree shape of made of the 2-to-1 serializer stages. So here, each 2-to-1 stages can be modeled like this, which is a typical structure. You have a set of retiming flip-flop or latches that will set the correct timing for the input of the mux. And this mux will select one input when the clock is high and the other input when the clock is low. Okay, this way, you have serialized 2 inputs into one, and the output now have twice the data rate. Okay, and you repeat that process at the next stage and so on to increase the serializing rate. Okay? There are more details in our tutorial. To operate, and you can continue this process to build the 8-to-1 serializer and a 16-to-1 serializer. And what you should note that each stage, each level of the serializer will require a different clock frequency. This is why this part cannot be synthesized, although it's almost fully digital. One is it works at really high frequency in the end, like it will generate 32 gigahertz output at maximum. But also each stage will require a different clock frequency. So the clock domain crossing is very tricky to handle in a typical synthesis tools. And so this will be done in a custom fashion. And to generate the clock frequency, the typical approach is you take the highest clock frequency, which drives the last stage, and then you use a set of frequency divider to generate the lower frequency clock for the earlier stages. So you need a set of divide by 2 stages. Each divide by 2 is basically a toggle flip-flop. Which you can build using a DFF X-bit primitive and the inverter X-bit primitive. Very simple. And you just cascade them to produce a set of clocks that has half the frequency, quarter frequency, and 1/8 frequency. Okay. Now, here's a simple test bench to see if the 16-to-1 serializer works properly, along with this frequency divider that I described. So to compose a test bench, we need to feed in 16-bit wide input PRBS data. And in the output, you have a serializer, serialized data, and you want to make sure that the 16-bit has been ordered properly to produce the final output. Well, to do that, you can use a primitive called PRBS gen, which produces a PRBS pattern. And one nice feature of that is it can produce parallel streams, like 16-bit streams. And of course, you can also choose the pattern length of the PRBS pattern. And the nice property of PRBS is that when you serialize the PRBS, you also get the PRBS with the same pattern. So you can use the measure_BR primitive, which checks the validity of the PRBS pattern of a given length. And it doesn't need to know whether it has been serialized or not, because it looks the same. That's very interesting. So we use these primitives to check the correctness of the serializer. The measure_BR primitive that I mentioned will produce these text log when the simulation is over. It will report the number of bits it has checked and number of errors it has detected. If the answer is 0, then it means things are working fine. Okay. Our UCI spec says we need to implement a P4 equalization in an TX path. Again, there are multiple ways. And one way we use is we implement the FFE in the serializer stage. That is, we have a control bit, and depending on the control bit, the serializer output can generate a stream for dn-1, which is the one previous data instead of the current data, and with the additional inversion. Okay, and this output will drive the final stage. So some of the driver will drive the inverted version of the previous bit, where some other driver will just drive the current bits, and with the mixing happening at the final output, you get the behavior of a one-tap FFE. Okay. So this is the serializer stage. We can either produce a D of n or D of n-1 bar. How does it work? When the control bit is 0, then it will select the path highlighted in red here, which is basically a 2-to-1 serializer that I mentioned before. But when that control bit is 1, it will now select a different path, which inserts one additional flip-flop or latch that will cause a 1 UI delay. And then these set of inverters will do extra inversion. So that way, the final output will be a dn-1 inverted. This is a quick simulation results that it works. In one mode, we're producing the data as is, and the other mode, we're producing the one UI delayed output with the extra inversion. Okay. So to build the final FFE, we're going to have a multiple segmented driver. So each driver is not just one driver. It will be segmented into a parallel of unit drivers. Okay, we'll use 16 of them. Okay, and among them, 3 of them will have an option of driving D of n or D of n-1 inverted. Okay, this way we can support a emphasis value of the 4 different values. Okay. Our spec says you can support just 1, but probably you need more. Now, that leads to a question of how do we do the final driver? The final driver is simply a voltage mode push-pull driver, which is also called the SST driver. And it has additional enable signal so that when the enable is low, it will leave the output floating. It will turn into a high impedance mode. And we prepared 2 types of unit driver cells that has different sizes. So one is just the basic size. The other one has 8x size. So basically, the only part that the size makes sense is this final part, which determines the output resistance. So the 8x driver will have 1/8 output resistance compared to the 1x unit driver. And each of our driver stage, as I said, is made of a parallel unit drivers. So we'll have 8x size unit drivers, and also another 8 of 1x unit drivers. And their outputs are all shorted together to drive the final output. So with this structure, you can achieve 2 things. One is you can adjust the output impedance of the driver. So our UCI spec says you want to keep the output impedance as 30 ohms, which is slightly different from other standards, which try to set it at 50 ohm, but that's what the spec says. And you can adjust that R out by enabling different number of units driving the output. So if you have more drivers, the impedance becomes lower. If you have less drivers, the impedance gets higher. Okay. And the other thing is you can control how many unit drivers are driven by the current bit, D of n, and how many are driven by the D of n-1 invert. That way, you can control the amount of de-emphasis, basically the tap coefficient for the TX FFE. And now we can put together the serializer stage, the driver, clock divider to have the Datapath model. Okay, and here's a quick simulation results. We are driving a fixed pattern of 1, 1, 1, 1, and 0, 0, 0, 0. And we're plotting the waveform with different FFE control values. You can see that the de-emphasis happens and the amount of de-emphasis changes. And this is a simulation with the PRBS pattern. And again, the de-emphasis works properly. Well, this is another check, making sure that we have connecting things up properly. And since with the VR is 0, we know we have done it correctly. Now, I actually mentioned the word data valid clock without really explaining it. And this is my chance of doing it here. So, as I said earlier, in UCIe, data is transmitted in units of frame. Okay, so when the frame starts, the clock's starting to toggle, and the valid will also toggle, but at a lower rate to indicate that the frame is now valid. Well, you have started the transmission of the frame, and the data transmitted during that period is valid. So take this as data, and if the valid is not toggling, then it's invalid, so they don't take it. Basically that. And there's some also special requirement that when the frame is over, the valid will stop toggling immediately, but the clock has to keep toggling for at least 16 UI or 16 UIs. This is a requirement to make sure that all the data that are still within the intermediate stages, like in the deserializer, can be flushed out. Okay. This is a requirement described in the specification. Now, to support these frame synchronization or framing, the easiest way for us to do is to pretend the clock driver and the valid driver are basically like a data driver. Okay, they're just sending data. Only difference is that their pattern is fixed. You know, for clock is 101010. For valid is 11001100. Okay, so I'm going to describe what the FIFO is, our FIFO model is, but this is going to take the actual data that are transmitted through the data driver. And we have a kind of a stripped down version of the FIFO, which will feed the pattern to the driver for the clock, driver for the valid with a fixed pattern. Okay, and that means for the clock and valid, we're using the same set of serializers, same set of driver. Maybe an overkill, but this is the easy way to complete our model. So one requirement that's going to be more apparent when it comes to the logical layer is that we have to adjust skew, the timing skew between the clock and data and clock and valid. We're assuming that, well, the channels for those different lanes are not well matched, and it has to be calibrated before you start the transmission. And that skew may span a wider range than one UI, especially at the highest data rate of 32 gigabit per giga transfer per second. Well, one UI is not that long. So it becomes very easy for the skew to span more than one UI. Then the problem is, hey, with using our phase interpolator, we can only adjust skew within one UI. But what happens? How do we adjust skew that's longer than one UI? So we need to get some help from the FIFO. That is, we need to shift the bits that we're going to transmit so that it can create an effect of making additional delay in units of UI. For example, let's say we want to delay the data signal and the valid signal respect to the clock. We will shift the bits sent to the data driver and the valid driver. Of course, we'll do the shifting based on a bitwise fashion, units of bits. In case we want the data and valid to have an earlier timing, maybe those will have longer delay. In that case, we'll delay the clock pattern. Okay, so one is what we call positive shift, the other is called a negative shift. This is a necessary requirement. By the way, this is not describing the spec. Spec just says you have to adjust the delay, and this is how we figured how to. Okay, so FIFO is nothing special. It's a Verilog block that implements a FIFO in a, I don't know, it's called a buffer-based FIFO. So on the left, you have a set of signals that control writing. So in the input data, when the write is enabled at the rising of the clock, you write your input data into a FIFO buffer. On the right-hand side, you have a set of signals for reading the data out of that FIFO. For example, at the rising end of the reader clock, if the enable is high, then the FIFO will read the data and drive its output. And the timing for the left side and the right side are completely independent. And this is what the FIFO does. It kind of decouples the clock domain between the both sides. Now, we need an additional capability on top of this basic functionality. That is, we need to be able to shift the phase. So even when the reader says, give me a data, you're going to pretend that, oh, I'll give you a 0 and first, and then start giving you the real data after some numbers, which is indicated by the shift code. That creates the effect of shifting the data and causing the additional delay in units of UI. And as I said, the sync gen block is a stripped down version of FIFO that produces a fixed pattern instead of the input pattern, instead of the general data pattern. And it has to support the same functionality, same bitwise shift. I guess there's a typo, so that it can adjust delay in units of UI. Okay. Now here's a model that has all those components. Like so, we started with the clock path that has a PLL, DCC inside, DLL, phase interpolator, and this will produce a set of clocks. And on the driver side, we have a FIFO for the data, sync gen for the valid end clock. They all produce patterns for the serializer stages and the final driver stages. So we have those sets for the valid, data, and clock. They're all identical, basically. Okay, so this will be the top level, the transmitter model for the main band transceiver. Now, here's a test bench for testing this transmitter part. These are the set of primitives that feeds the stimuli for the DUT, and then we have the output for with the actual channel. So, short note on the channel model. The channel model that we use is actually a transmission line, which is one of our circuit primitive, and you can extract the characteristics from the actual channel by taking the S parameter. Well, I'm not saying that the X model can run directly with the S parameter model. But you can do it by, converting it into a more XModel friendly format using these scripts called SParam to TF or XParam to T-line scripts. Then it will produce some data file, let's say channel.data, DAT. Then it can take it as one of the argument, and when it runs, it will read in that file, see what kind of channel characteristics you need to model. And this primitive will work as a transmission line. For example, it will have a finite delay from input to output. There will be a finite loss between input and output based on this characteristic file. And also, it has a characteristic impedance so that if the impedances are not matched, you get reflection. And in case when you have multiple lanes in your channel, you can also model crosstalks. Okay, so this is just a simulation with the PRBS pattern with the variable de-emphasis degree. And this is the simulation results confirming that our valid framing works. For example, when the data is finished, when the frame is done, valid stop toggling, the clock keeps toggling for 16 UI period, and then it becomes 0. Since we have added the channel, we can observe the eye diagram at the output of the channel. This is actually the eye diagram without the FFE, with the FFE disabled. The bottom one is the eye diagram with the FFE enabled, and you can see that the FFE does improve the eye opening. Wow, I'm already out of time. But if you, okay, let me see if I can answer some quick questions. Okay, so Vic, question from Vic is, this looks like this tool can analyze other types of serial links. How about ASA SerDes? Yes, it is possible. And I kept mentioning the high-speed I/O tutorial, which gives a tutorial on how to model high-speed interfaces in a more general setting. So that will be a good reading material. And of course, you can model PAM4 SerDes. We do have example of a PAM4 SerDes in the context of ADC-based receiver. And the last question from Vic is, you want to mix cadence schematic blocks along with the system level blocks. So it really depends on what you mean by the cadence schematic blocks. If the cadence schematic blocks is a circuit schematic, the real circuit schematics, then you have to use the AMS, the cadence AMS, which supports the mixed mode simulation, like the co-simulation between SPICE and Verilog. That's the only way of doing it. The problem with that is because of the difference of the two simulators, the simulation is not that fast, which is actually serve as a strong motivation for us to move all the analog part into SystemVerilog so that you can run both analog and digital simulation in one platform. That's the way we go. Okay, so let's move on to the receiver. So receiver won't be as long as the transmitter because it's relatively simple. The receiver also has two components. One is the clock path, which generates the clock. Basically, just recovers the clock based on the forwarded clock from the transmitter. And then it has the data path, which samples the data using those clocks and recover the digital data and deserializes them. Okay, so this is the high-level model of the RX data path. You have a set of samplers, or you can call clock comparators, that will clock using the 4 phases of the RX clock. So it's a so-called quarter rate sampling receiver. Okay, and each receiver will need a reference level. So it's a single-ended transmission, so that to tell the difference between ones and zero, you need to compare the sample voltage against some reference in the middle. Okay, so if the voltage is higher than the reference, it's 1. If it's lower, then it's 0. And then you get the stream data, which is already deserialized into 4 streams, and you take additional deserialized stages to produce the 16 parallel streams at the output. And again, this deserializer will need a set of clocks with different frequency, and you can produce them using the clock divider. This is what the quarter rate receiver front-end model looks like, the first block in the previous slide. Again, you have a set of clock comparator. These are compare primitive, which are triggered by different phases of the RX clock. Okay, and each of them are comparing the input against the reference voltage, which is controlled by some digital code and also scaled by some voltage called VSW. Okay, and basically when each compare primitive will sample the 2 inputs at the rising edge of the triggering clock, and when its polarity is high, positive, it produces a 1, and the polarity is negative, it produces 0. You have this additional latch or D flip-flop at the output of these comparators to realign the timing of their outputs so that they all fit in the same clock domain. Let's say our clock underscore RX of 3. So the digitally adjustable reference generator is nothing but a D to A converter. So it takes a 6-bit input. I thought it's okay. I think it's 4-bit input and produce the analog output. And we want this to scale with the swing voltage, which actually sets the swing level for the transmitter, so that the adjustable range of the reference voltage and the adjustable range for the swing can track each other. So we made it so that the adjustable range is between 0 and 0.625 times the VSW, because 0.625 VSW is the maximum swing considering the input, the driver impedance, and the termination condition. And typically the reference will sit in the middle. So we have a nice range covering both positive and negative side. Serializer is again a tree-type serializer, cascading these 1 to 2 deserializing stage. So each stage is a half-rate receiver. So if there's input, you sample it at the rising edge of the clock, or it's actually falling edge of the clock, and the rising edge of the clock. And for the one with the earlier phase, you delay so that the output streams are realigned. That's the 1 to 2 deserializer. And by cascading them, you get higher rate of deserialization. You need clocks. So in UCIe, you just directly forward the clock from the transmitter to the receiver. And the clock is transmitted in a differential signal. So you have a pair of differential signal coming in, and use some sort of a differential amplifier to produce a clock signal inside. And then you use a block called phase generator to produce a 1/2 rate, 1/2 frequency, but 4 phases of that clock, which drives those set of clock comparator that I just mentioned. The spec says in case this differential clock doesn't work or doesn't properly propagate to the receiver side, you use this kind of a redundant lane, which is like a backup channel called track, and you use the track signal as a clock. Okay, so the forwarded clock is differential, whereas the track signal is a single-ended. So you need 2 kinds of limiting amplifier to take the analog signal and produces the full swing digital output. For the differential clock, it's nothing but a slice primitive that takes the differential input and produces the digital output. And we just added additional buffer and inverter to produce the true and complemented version of that clock. For the single-ended input, again, you need a reference, and that reference can be digitally adjustable, and you use a slice primitive to produce the output clock. The quarter-rate clock generator is nothing but a clock divider, just that you tap the middle points and also generate the true and complementary version values of that of those middle points, so that you get a 4 phases clock, while the clock where each of the clock has the 1/2 frequency of the input clock. Now, see, the receiver is short. Here's a top-level receiver model. So for the receiver, for the clock inputs, where is it? Here. For the pair of differential clock, you have a limiting amplifier that recover the clock. And then after the phase generator, you have 4 phases of the half-rate clocks. And those clocks will drive the receiver for the data and the value. Okay. And at the output, you get a 16 parallel deserialized output, which are fed into the FIFO, and the logical layer will take the output after the FIFO to do the additional processing. Yeah, here's a testbed setup for this receiver. X1 stands for that we only have one data lane for simplicity. And this is a check for the deserialized stage, whether you have ordered, deserialized in the proper order it's quite often I make a lot of mistakes there. So I always do the check here. And now, since we have a transmitter and receiver, now you can put them together through a channel, see if it works. Okay. Again, you can now do an end-to-end check, see if the data are transmitted without the error. Again, we're using a set of PRBS gen and measure BER primitives to perform this BER test. And here's the eye diagram that we can observe at the channel. Looks the same. It should be the same as before. Although because of the limited time, I cannot cover everything here. XMODEL is capable of statistical simulation. It's very similar to a transient noise analysis, but it has some limitation. But it's extremely useful for measuring or estimating bit error rate of a high-speed interface like this, because it can estimate a BER of a given link down to like 10 to the minus 20th. So these red line are not interpolation. They are directly simulated data using the XMODEL statistical analysis. On the other hand, if you use a straightforward Monte Carlo analysis, you can only estimate down to, let's say, 10 to the minus 3, which is not low enough to get the proper measurement. Anyway, there is that capability, and we are measuring the BER while changing the phase interpolated control bits from 0 to 63. And we see two openings because this whole range span one clock cycle, which contains two UIs. So you're supposed to see two openings here. And you can do a similar measurement while sweeping the reference voltage. And that gives you a measurement on how wide the voltage margin is of your transceiver. Okay, now we can put together a UCIe electrical layer module. And to do that, we need to have this sideband. Okay, so far we talked about the transceiver for the main band, which contains the data lane, clock lanes, valid, and track lanes. And you have two sets of those for going forward and backward. Okay, sideband transceivers are for exchanging some auxiliary messages during the training process, and they operate at a much lower rate of 800 megahertz. But we still need those transceivers to complete the whole PHY layer. But the sideband transmitter and receiver are very, very simple, and for their modeling, we can recycle many of the components we already discussed. For example, the sideband transmitter is just a simple FIFO with the final driver. There's no serialization required, and there's an additional capability for the clock gating. And the receiver is just we cover the clock by limit amplifying, and then you sample the input using a flip-flop, for example. And you have FIFO. Now, we have main band transceiver, sideband transceiver. You put them together, you get the whole electrical layer. Yay. All right, and now you put these two electrical layer model through the channel, now get a pair of UCIe electrical layer.